Hello everyone, my name is Aiping Xiong. I'm an assistant professor in the College of Information Science and Technology at Penn State University. In this talk, I will present our work towards effective differential privacy communication for users' data sharing decision and comprehension. This work is done through collaboration with graduate student and faculty members from Purdue University and the University of Wisconsin-Madison. To protect the data privacy and ensure utility in the data publishing, the concept of differential privacy has been proposed. The initial technique proposed is called DP or central DP. Visually speaking, central DP adds extra noise to users' information at an aggregate level. If a strong adversary knows all records but one user's information in the dataset, he or she is still unsure about the user's specific information with the added noise. In recent years, local differential privacy or LDP has been proposed. LDP differs from DP in that random noise is added at an individual level before sending the data to the server. Thus, on the LDP, users do not need to rely on the trustworthiness of the company or the server. Recently, DP and LDP techniques have been deployed by government agencies and high-tech companies. For example, the 2020 US Census is deploying DP to protect the privacy of the surveyed population. With the increasing deployments of DP and LDP techniques, an interesting and important open question is whether users can understand these techniques and consequently increase their data disclosure when they were informed of the differential privacy deployments. Our work takes a step towards understanding how to effectively communicate DP and LDP techniques in order to facilitate users' data sharing decisions and their comprehensions of differential privacy techniques. Centering on textual description of differential privacy techniques, we set out to answer two questions about users' data sharing decisions initially. First, will users increase their data disclosure, especially for high sensitive information, when they were informed that DP or LDP techniques have been deployed? Second, to what extent will participants' data sharing decision depend on how the privacy techniques are communicated? For example, description focus on definition or implication. We conducted two experiments to address those two questions. To address the first research question, we vary the presence and absence of DP or LDP in experiment 1. We present different ways of describing DP or LDP in experiment 2, addressing the second research question. In each experiment, participants made hypothetical data disclosure in a health app survey setting. Participants were asked to imagine that they just install the health app, which needs to collect personal information from them. They were then shown 14 questions asking for personal information, among which half are considered low sensitive and the other half are high sensitive. Experiment 1 was conducted on Amazon Mechanical Turk. We recruited about 600 participants. There were 4 between subjects conditions. The control condition was served as a baseline. We chose to mention the benefit of data sharing in a game framing as it is often emphasized in the wild. DP and LDP conditions were the same as the game framing condition, except an extra description of DP or LDP was presented before participants made the data sharing decisions. DP and LDP are typically used in different settings. Each participant in our study was exposed to only one of them. In terms of privacy, LDP provides stronger protection than DP does because LDP does not need to trust the server. In this case, we expect a high data disclosure rate on the LDP. When that did not happen, it could be an indicator that participants do not really understand the nature of the protection from the descriptions. To come up with the descriptions of DP and LDP to be used in our study, we started from the description published by the companies and organizations that deploy those techniques, and then conducted multiple internal discussion and reviews. In the discussions, we involved experts of differential privacy to ensure our description of DP and LDP are technically accurate. As mathematical rigorous is one key strength of DP and LDP, we decide not to shy away from using mathematical terms such as aggregated data or probability in the description. Description in experiment 1 focus on definition. We also include the company and organization names associated with the DP or LDP deployment. For the data sharing decisions, each question with its options were presented within a smartphone layout. Participants were instructed that their task was to read the survey question, decide their answer to it, and select how they would like their answer to be used. Note that we didn't ask participants to actually review their personal information. For each question, participants were asked to decide whether they would like the data being used locally only, or both locally and at the app server. We also provide options of opt-out and prefer not to answer. In this talk, we focus on the results of both options, which directly reflect participants' willingness of data sharing. The 14 questions were presented in a randomized order in each condition. After answering those 14 questions, participants completed a questionnaire that asked for their demographic information. We calculate the both option selection rate collapse across participants in each condition. The results were then entered into chi-square tests with one within subject factor, the information sensitivity, and one between subjects factor, the condition. Results in this slide were presented with condition as the x-axis and the both option selection rate as the y-axis. Dashed blue bars indicate the results of the low sensitive question, and a solid orange bar indicate the results of the high sensitive questions. We obtain a main effect of question sensitivity, and the effect was significant for all conditions. The main effect of condition was also significant. Post hoc analysis revealed that all the pairwise comparison was significant except for game framing versus LDP and game framing versus DP. Moreover, we obtained the two interaction of information sensitivity and a condition. For the low sensitive question, the largest data sharing rate was obtained for the game framing condition. In contrast, for the high sensitive question, the selection rates for the DP and LDP conditions were higher than that of the game framing, indicating the effect of differential privacy communication. To summarize, in experiment 1, participants showed more privacy concern for the high sensitive information than for the low sensitive information. When they were informed of DP or LDP protection, their overall data sharing did not change. However, they increased their data disclosure for the high sensitive question, indicating a positive effect of communicating DP and LDP. The overall data sharing rate of the DP condition was larger than that of LDP condition, indicating that participants did not understand the better protection of LDP. To examine factors that affect the DP and LDP description in users' data sharing decisions, we conducted two sub-experiments in experiment 2. The procedures of experiment 2 were the same as experiment 1, except for DP and LDP descriptions, which is the key manipulation in our study. In experiment 2A, we emphasize that the data perturbation process of LDP happens before sending data to the server, and examine whether participants would understand the better protection and thus increase their data disclosure. We also include the definition description from experiment 1, but we remove the company and organization names associated with each technique to understand their influence on participants' data sharing decisions. Results were organized and analyzed in a similar way to experiment 1. Besides the main effect of the information sensitivity, we also obtained the two interaction of information sensitivity by condition. However, participants seem to show less willingness to share the high sensitive information with the LDP descriptions than with the DP description, indicating the minimum effect of an emphasis on data perturbation process of LDP. Considering the difficulty for layperson to relate data perturbation with privacy protection, we examined the effect of communicating the implications of DP and LDP techniques in experiment 2B. Specifically, we made it clear to participants that protection provided by DP relies on the trustworthiness of the company or the server, while LDP does not. We also included one LDP implication without local condition to examine any impact of the word local on participants' data sharing decisions. Results were also structured and analyzed in a similar way as prior experiments. This time, not only the main effect of information sensitivity, but also the main effect of condition was significant. More critically, as shown in the figure, more data sharing were obtained for the two LDP implication conditions than for the DP implication conditions, regardless of the question sensitivity. To summarize, across two experiments, we used the Health App data collection setting and hypothetic willingness to disclose sensitive personal information as a test bed. So data sharing decision results suggest that participants have difficulty in understanding the definitions or the perturbation process of differential privacy techniques. However, description of the implication are effective. On average, participants' data disclosure rates of the high-sensitive question were 20% less than the low-sensitive question, revealing that information sensitivity is an important moderator for people's data sharing decisions. We further conducted two experiments evaluating participants' subjective and objective comprehension of DP and LDP. Participants' stated comprehension of the descriptions were good in general, and they highlight parts closely related to data perturbation process as the most difficult part to understand. We also identify various factors impacted their data sharing decisions with DP or LDP descriptions. Due to time limits, in this talk, we skip subjective comprehension measures in experiment 3, but focus on participants' comprehension performance, the objective comprehension measures in experiment 4. Experiment 4 was also conducted on Amazon Mechanical Turk. Besides the description focus on definition and implication from prior two experiments, we also proposed a flow description for each technique. Specifically, we introduced DP or LDP data flow by listing different parties, such as external third-party company, and explain how those parties are involved in the data flow. Thus, in the new descriptions, the risk of data compromise for DP or LDP was implied but not described explicitly. We also added the description of accuracy loss in affording utility inference. We evaluate participants' comprehension of DP or LDP with 5 questions. 3 of them were about privacy inferences from the perspective of attacker, internal employee, and third-party companies. Another 2 were about utility inferences from the perspectives of the app company and the third parties. Participants were randomly assigned to one of the 6 descriptions. After viewing the Health App data collection setting and one description of DP or LDP, participants answered the 5 questions which were presented in a randomized order. For each question, correct answer rate of each condition were calculated and entered into chi-square tests with 2 between subjects factor, the description and the technique. Results in these slides are presented with the condition as the axis and the correct answer rate as the y-axis. We use light pink bars indicating the results of the without name description, light green bars presenting the results of the implication description, and light blue bars showing the results of the flow description. Dash bar indicate the results of the DP technique, and the solid bar indicate the results of the LDP technique. Across all the 5 questions, the main effect of description was evident. Specifically, for all privacy-related questions, correct answer rate of the implication description were larger than those of the without name descriptions. Moreover, the best results was evident for the flow description, except for the privacy inference of the attacker, which is the first question in this figure, which show the best results with the implication description. We also obtain a two-way interaction of description and a technique for all privacy-related questions. Specifically, results of the LDP conditions were better than the DP conditions with the flow description, but not with the other two descriptions. For the two utility-related questions, the best results were evident for the flow descriptions as well. However, there is no significant difference between the other two types of descriptions. To summarize, in experiment 4, with descriptions focused on definition, participants show they have difficulty in understanding the implications of DP or LDP. Explicit description about the trustworthiness of the company improve the correct answer rates for privacy inference question, especially the inference about attackers. Thus, the comprehension results of experiment 4 were consistent with the data sharing results that we obtained in prior experiments. Participants' correct answer rate for all questions will include with the flow description except the inference about the attackers. Those results indicate the effect of description affording implication inference and highlight the importance of explicit description in helping lay people to understand differential privacy. In conclusion, across different approaches of textual description, our study shows that descriptions affording privacy and utility implication can facilitate users' data sharing decisions and or their comprehension of DP and LDP techniques. The effect of information sensitivity on people's data sharing decisions implies different distributions among the collected online information, which is informative to the differential privacy algorithm or deployment. Overall, our work highlights the importance of user-centered deployment of differential privacy. In the end, I would like to thank all my collaborators, Tianhao Wang, Drs. Ninghui Li, and Somesh Jha. Our work was also partially supported by NSF awards.